Okay, so we agreed with
Okay,
Joao that...
so welcome everyone, those who were active participants of this workshop and those who just crashed the party for the last cookie of the day, and so we're very happy to finish it with a discussion session, which is going to be by Lorenzo and Joao about 6 points of 5-dimensional gauge theories.
Okay, thank you. Thanks a lot for the invitation. So I will start the discussion with some introduction and motivation, and then I will tell you about my work done in collaboration with Fabiana De Cesare, who is a student in SISSA, and Marco Serone, and then I will leave to Joao. Okay, so the starting point, let's say the motivating question, is a question regarding the classification of consistent quantum field theories, or more specifically conformal field theories, which is whether there exists any conformal field theory in 5 or higher dimensions without supersymmetry. So in this talk, as the title suggests, I will focus on 5 dimensions. And just to review, the reason why this is a hard question is that our favorite tool to construct interacting conformal field theory, which is to start from some free field theory and then turning on some interaction, relevant interaction, and then flowing down possibly to some fixed point. So this tool is simply not available when we are in 5 dimensions, simply because all the interactions we can write down are all irrelevant. So if we turn them on, we simply flow back to a free field theory. On the other hand, we do know examples of conformal field theories in 5 dimensions with supersymmetry. And the reason, let's say, they evade this difficulty is because they are based on string theory constructions. And I just want to remind that some of the most well-studied examples of these superconformal field theories are indeed UV completions of supersymmetric gauge theories in 5 dimensions. Okay. Oops. Let's see. Okay. So a promising setup to look for these fixed points in 5D is that of non-abelian gauge theories. So let's start by defining them. So they are defined by the usual Yang-Mills.
Can I ask a question? So you said that these SUSY examples are UV completions of SUSY Yang-Mills. That means that you can flow from them to SUSY Yang-Mills?
Yes, I said SUSY Yang-Mills, but actually I should have said also QCD. Like the simplest examples were constructed by Seiberg. They flow to SU2 gauge theory coupled to NF flavors in the fundamental, and they exist when NF is up to 7, if I remember correctly.
But I guess I mean where they flow, it depends on how you perturb them. So you can turn on various perturbations. Suppose that you turned on some SUSY break-in perturbation in this 5-dimensional SUSY SCFTs, then where do they flow?
Yeah, well, what I was mentioning is that there is a SUSY preserving deformation, which basically maps to the gauge coupling of the gauge theory. Then you're totally right that this is not the only relevant deformation of these fixed points. For instance, there will also exist SUSY break-in deformations, and I don't think we know exactly what is all the phase space in presence of these SUSY break-in deformations. In fact, I will mention later in the talk that recently there has been some proposal for how to construct these fixed points, also based on these SUSY break-in deformations.
Okay.
So a promising setup is that of non-abelian gauge theory. So this is just defined by the usual Yang-Mills Lagrangian. And then, of course, we can also consider, in principle, coupling to matter fields. And the argument that I just mentioned also applies here. So this G square is dimension of an inverse of an energy. So strictly speaking, while looking at this Lagrangian, we should just interpret this as an effective field theory, okay? So G squared sets, in a sense, the UV cutoff of the theory. Below this scale, the description in terms of a gauge theory is valid, and it breaks down when we try to go to energies above this scale, and we just don't know. We just don't know what's going. I mean, we just cannot use this description for higher energies. So the connection to the question that I started with is that, of course, we want to explore the possibility that actually in the UV there exists a interacting UV fixed point. So what does that mean more precisely? It means that we want to ask whether there is a five-dimensional interacting conformal field theory which has a relevant deformation, which in the IR maps to the inverse coupling squared, and it flows to this effective field theory given by the gauge theory. We can also ask this question in a slightly more restrictive way. We can say that we want to know if such a CFT exists for which G square is the only relevant deformation. And so if we are in this more restrictive setup, then we would have a very simple phase diagram as a function of the gauge coupling squared, in which there is for small coupling, there is the gauge theory phase. Then as we crank up the coupling, at a certain point, we hit a second order phase transition. And then on the other hand, on the other side, we don't really know what there could be. Like, I mean, a very natural speculation could be that this would be a confinement, deconfinement kind of transition, second order transition, in which the gauge theory phase is the deconfined phase. And then on the other side, there would be some mysterious confined phase, which could be gapped or I don't know what. Okay. So that's the question we want to explore. So what are the methods that can give us some hint that this fixed point might exist, or more generally the methods that we can use to study this problem and maybe rule out this possibility? So the first and most straightforward and direct hint that such a fixed point could exist, I think it's fair to say that it comes from epsilon expansion, which is what I will tell you about in the rest of my talk. Then, of course, we can also try to explore this question using lattice simulations, and this will be the topic of Joao's remarks, so just hold on a few minutes. And exactly, I mean, this addresses Slava's question. Like, recently it was also proposed how to construct such a CFT by studying the phase space of the supersymmetric conformal field theory when we also deform by non-supersymmetric, by supersymmetry breaking parameters. So this was done in a paper by these authors. And of course, another possibility is to try to tackle this problem using the numerical bootstrap. For instance, there were some attempts in the paper by Zijing and David. I think it's fair to say that at the moment there is no like clear-cut strategy for how to use the bootstrap to like try to address this kind of question, but of course there could be in the future. And perhaps there are also other methods that I'm not aware of.
So can I ask, yes, does the SCFT always have more than one relevant operator?
More than one, you asked?
Do the SCFTs always have more than one relevant operator?
Yes, so I think the particular one that they considered, so there are also flavor symmetries of this, sorry, global symmetries, I wanted to say, of this SCFT. So you also have the luxury of choosing relevant deformations that breaks supersymmetry and preserves some subgroup that you like of this global symmetry. So indeed, what they considered was not the most generic supersymmetry breaking deformation. They considered one that preserved a certain subgroup. So there are even more in principle. So but the phase space, of course, becomes more and more complicated if you start adding more and more relevant operators. So it might be harder to say something. Okay.
So on your previous slide, the putative CFT cannot be an S. The putative CFT that you've sketched here cannot be an SCFT. So,
well, if I don't add this more restrictive requirement, then actually, in a sense, we know that the answer is yes, because I can start with the superconformal field theory and turn on the supersymmetry breaking deformation and G squared, and that will flow to Young-Mills.
Yes.
But how do we know? I mean, do we know that?
Well, let's say it depends on the hierarchy between the two relevant couplings. Suppose that I turn on the gauge coupling much larger than the supersymmetry breaking mass, let's say, then, okay, it's not fully rigorous what I'm saying, but I imagine that I first flow to a phase which is very similar to super Young-Mills, and then the supersymmetry breaking deformation will be just a mass for, let's say, the gauge genus, and then I just flow to Young-Mills.
Okay.
Yeah, no, that seems possible. But that's why I was asking. So
yes,
there are no SCFTs known with a single relevant deformation.
Right. In that case, you need to turn on two at the same time in order to flow to Young-Mills. So it doesn't fall in this more restrictive.
Okay. Thank you.
Okay. So these are the methods. Okay, so let me now explain.
But I'm sorry, Lorenzo, just to finish this about CFT. But what exactly did these guys do? They said that if you turn on several of them, then you can actually flow.
Yeah. Okay.
Not
Well,
to the Young-Mills,
actually,
but to some intermediate. Are you going to talk about this?
I have a backup slide that.
Okay, maybe we can postpone it to the backup.
Yeah. Okay. Fine. But so at the end, maybe I can show you this backup slide. So let me now explain the method that we actually use, which is epsilon expansion. So the idea is conceptually very simple. It's completely analogous to when we study the Wilson-Fisher fixed point. So it's simply to consider the gauge theory, the non-abelian gauge theory in 4 dimensions, and do a continuation from 4 dimensions to 4 plus 2 epsilon. Okay, for some reason we like 2 epsilon instead of epsilon. I apologize for that. And then when we do that, the beta function is going to acquire this term linear in the coupling. That's simply telling us that the coupling becomes irrelevant. And famously, the one loop term is negative, and at least if we don't have too many flavors. And as a result, we can find a weakly coupled UV fixed point, which is under parametric control when this parameter epsilon is very small, where G squared at the fixed point is of order epsilon. And this was first pointed out by Peskin in a paper of 1980. And here I just illustrated what we would like to do. So what we would like to do is that we would like to start from close to 4D, in which this UV fixed point is under perturbative control. And somehow we want to try to extrapolate to see if this fixed point survives until 5 dimensions, okay? And in order to do this extrapolation, we need to necessarily use some form of resummation of the perturbative series and to try to extrapolate, okay? Oops, sorry. So let me mention that like previous to our work, the most updated analysis was done by Morris in 2004. So what he did is to use the then available for loop results and use a technique called optimal truncation, which, okay, if you don't know what it is not important. Perhaps if there is time, I will tell you some more technical details later. And his result is that he found evidence for the existence of this fixed point up to 5 dimension for pure Young-Mills. So strictly speaking, he did it for SU2, and he did it in the limit in which the number of colors goes to infinity. And then he said that since in both cases he found evidence, presumably it works also in between. And in the meantime, this group of people, there were many papers on different aspects of the problem, published also an impressive perturbative result containing the 5-loop beta function and mass anomalous dimension for a generic non-abelian gauge theory for dimensions with fermions. Okay, with fermions in some arbitrary representation of the gauge group. Okay, so let me ask myself some questions. So why do we reconsider this problem now? So there are basically 3 motivations. The first one is that the obvious one, that we can update it with the 5-loop results, and also we can use a slightly more sophisticated resummation technique. So we use Borel-Padé. And also what motivated us is that there are new results coming from the lattice. That is what Joao will talk about. And also this new proposed construction from the superconformal field theory. So that this is what led us to reconsider the problem. And another question that you might ask is, of course, can we trust this method based on a extrapolation of perturbation theory? And especially you might be worried because unlike the more familiar cases of Wilson-Fisher or ON models in four monosepsion dimensions, here we are even doing it to approach a UV fixed point rather than an IR. So this seems even less under control. Here, I mean, I cannot offer any particularly clever comment. Indeed, I think it is good to be cautious with such extrapolations. On the optimistic side, I just want to mention the analogy with the, with 2 plus epsilon dimensions, in which we can consider, for instance, the Gross-Neve theory or the nonlinear sigma model. And in that case, we do know that the extrapolation is correct, meaning that we find a fixed point in 2 plus epsilon, it is a UV fixed point. And when we extrapolate to 3D, it corresponds to an existing conformal field theory. And we can even use these extrapolations to try and predict some observables. In this workshop, there was also the talk by Yin Chen, who used the similar 2 plus epsilon fixed point to learn something about 3-dimensional gauge theory. So this is like a well-established setup, and conceptually it's not so different from studying the non-abelian gauge theory in 4 plus epsilon. So we can hope that similarly it's also good in 4 plus epsilon.
Can I just ask a question along those lines? So
yes,
you said Morris did optimal truncation, which basically just means he's keeping some terms in perturbation theory. What yes. You said he did some non-trivial check. Like, what is there, and what could have gone wrong in if you're only keeping terms in perturbation theory? Like, what could have gone wrong? How could it have? Was there a chance that it could have been?
Mainly the check that you can do, the main check that you can do, which is also the one we do, is to check whether G squared is positive. So the thing that can clearly go wrong is that you can get negative G squared.
Okay.
So, yes. Does it answer, or you had another part of the question, or?
No, yeah, I was just, it seems like doing Padé-Borel is significantly better because you have a chance to see something beyond perturbation theory. But yes. But no, you answered my question. Okay.
So now I decided to present the thing in this order. So first I will show you the result, and then I will tell you the technical details. But of course, if it's not understandable, I can also invert the order. So what we did is that we considered to be definite SUNC gauge theory with an F fundamental Dirac fermions. And here I selected some of the main results. So for instance, for the case of SU2 Young Mills, so pure Young Mills without any flavors, this is what we get for the extrapolation. So sorry, I should mention that this A just means G squared is the notation that we use for G squared. So it's the gauge coupling squared. And what you see in this plot is in tones of gray are the perturbative results. And then you see the various adhes that we can use to approximate the Borel transform. And then for one particular adhe, which is the 2,2, which we selected as the best one based on some criteria that I can explain, we also gave an estimate of the error. And we claimed the evidence for the fixed point in the when this error bar does not include 0, okay? So in this case, we see that I'm extrapolating to epsilon equal 1/2, which corresponds to d equal 5, and the value for A is not compatible with 0. So we think this is evidence for the existence of the fixed point. And of course, later I will give more details about also the estimate of the error.
But this error seems to be very conservative because it like includes everything, and most of the curves are actually much closer to each other than the error. So why is it so conservative?
It is a bit conservative, but on the other hand, it doesn't look so conservative for all the observables, and we wanted to use the same method for everything. Okay. And I think so. Yes, in this case, it's true that if you look at all the central values of the different Padhe approximants, so if you, for instance, more naively just say that the error is given by the spread of the Padhes, then it looks much smaller than our estimate. And yes, and this error also includes basically all the perturbative results, even though, I mean, you see that the central values of the Padhe are much more well behaved than perturbative results. And here actually, well, okay, maybe I will return to this when we go to the various components of the error, but the thing that dominates it is our estimate of the non-perturbative error, okay, rather than the convergence of the Padhes.
Okay.
Okay. Then here what I'm showing is that the value of the coupling at the fixed point for Young-Mills and different values of the number of colors now. So we have a similar evidence to the one I just showed for keeping the flavor, no flavor, so pure Young-Mills and the number of colors up to 4. And similarly, we studied SU2 and increasing the number of flavors. And we also have similar evidence when NF also goes up to 4, okay? So what happens when we are 5 and above for both these parameters? What happens is that the error bar starts including 0, okay? So we are not claiming that we have evidence that, for instance, Young-Mills with NC equal 5 is not conformal. We are just claiming that with our error estimates, we cannot say for sure that it is, that there is a fixed point, okay? So these are the values that we see as a function of the number of colors. Now, the gauge coupling at the fixed point is not an observable, right? It depends on the scheme one is using. So we also wanted to look at some observables that perhaps can also be useful to compare with lattice simulations or other methods. So we looked at 2 scaling dimensions. One is the scaling dimension of the gauge kinetic operator, which of course is just given by the derivative of the beta function at the fixed point. So knowing the beta function, we can readily obtain this. And here I'm just showing to you the result for the SU2 gauge theory as a function of NF. And in the paper, you can also find similar plots as a function of the number of colors. Of course, we're also giving we're only giving the values for those values of the color and flavor for which we claim to see a fixed point. And similarly, we also considered in the theory with masses, for the theory with fermion, we also consider the scaling dimension of the fermion bilinear. I just wanted to mention, I forgot, that, okay, here the error bars are rather large, unfortunately, but one comment that I wanted to make is that this anomalous dimension is of order 1, so it's rather large. And so this, if you want, you can take it as a measure of the fact that this CFT appears to be rather strongly coupled.
Lorenzo, just to see if I understand your convention. So the dimension is 5 minus
5 plus this. Yes, 5 plus this number.
So it's about 3.
Yes, it's about 3. Yes.
So you're above the unitarity bound because you.
Yes, I'm above the unitarity bound. Yes, I'm above the unitarity bound. The full bar is above.
Yeah, Lorenzo, if you were to do the same thing for one of these supersymmetric theories that only exist up to 8 flavors, could you see evidence that something goes wrong for more than 8 flavors from just the 4 plus epsilon expansion?
Actually, already for 4 flavors, you'll be in trouble, right? Because there's no UV fixed point in 4 plus epsilon dimensions. The theory is asymptotically free for an F smaller than 4.
Including scalars?
I'm talking about n equals to 2 coupled to hypermultiplets.
Okay, thank you. Thanks.
Yeah, I was thinking that I should use n equals 1, but of course that's wrong. I should use n equals 2. So you're saying that it's 2
n equals 2, and then of course you can only do this for an F smaller than 4.
Yes. The one loop beta function is 2 and c minus an f. Okay, yes. When I thought about it, I was thinking about n equal 1. So yeah, that's a good point.
But n equal 1 will not extrapolate correctly to 5 dimensions. So you need to do n equals to 2.
Yeah, I understand. You're right. Well, on the positive side, I mean, when epsilon expansion sees something, that something exists. I mean, it would be more worrisome if it was the other way around.
But yes, I mean, that would be an excellent thing to try, right? Because there we really have an expectation that this fixed point should really exist in 5 dimensions.
Right. That's true. One should do that, and I agree. Yes, that would be a good check of the method to see if one gets perhaps some scaling dimensions are known, and one could try to check that. I mean, sorry, there is actually, now I remember, I thought about doing this at some point, but unlike the non-supersymmetric case, I don't know such high loop order results for the beta function in the supersymmetric theory.
The beta function in some scheme, of course, is just 1 loop exact. I'm not sure whether that's good enough for you. But...
Right, that's true. Yes, in principle, I could also just use those schemes. I mean, of course, I was thinking about doing it in MS bar. In the case, I don't know the result. But you're saying, okay, you should not care about the scheme, just doing it in the scheme in which it's 1 loop.
Then, of course, you have to compute the anomaly. The anomalies I mentioned, of course, are all order. They get contribution from all order. So
right. So, for instance, the only observable I could easily check, perhaps if I use this scheme for the beta function, would be the one of the gauge kinetic operator. But I think I would have trouble to try to check this. Okay. Sorry. Maybe I should continue at this point. So how am I doing with time?
Is there any reason why for psi bar psi the error grows with an f, while for f squared it's pretty stable with an f?
I don't have a very good answer to this. One thing that I can say is that this observable is the gauge kinetic term is the only one in which actually our errors are dominated by the convergence of the reconstruction of the Borel function, while in the other cases they are dominated by our estimate of the non-perturbative error. So that maybe explains why there is a different behavior.
Okay.
Do you happen to have similar results for trace f cubed? Just to check that remains irrelevant.
Okay, so there are some results for 1 loop anomalous dimensions of dimension 6 irrelevant operators in Young-Mills in 4 dimensions, but they're just 1 loop. So
okay.
At least that's what I found. It could be that there are more and I didn't find. So there is a paper by Gracie that discusses the mixing between dimension 6 irrelevant operators in Young-Mills in 4 dimensions.
That might be one of the things that the lattice might interest the lattice people if this anomalous dimension is large and negative.
Oh, well,
You
okay.
might-
So the one loop result is available, but I'm not aware of higher order.
But
And-
already, what's the sign of the one loop results, right? Is there a guy with negative anomalous dimension? You might just get an order of magnitude. Of course, it has to come down a lot, right? To be relevant in 5 dimensions.
You
Since you already have.
you're
all
worried
of
that they
these-
could become relevant. That's the thing that worries you.
I think that would be the most interesting question. Since you have all these results, it might be worth checking it.
Yes, okay. I didn't do this calculation, but I mean, it's also not something that you see immediately because it's a matrix of mixing between many operators.
Ah,
that
yes.
it picks. But yes, in principle, it can be checked.
Right.
Okay. So depending on how I'm doing with time, I could also go a little bit fast or skip some of these technical details. And so when did I start? So let me check the time. Yeah, maybe let me go fast on this. So I will not give you the technicalities of how we did the extrapolation unless you ask. Let me go fast. And so yeah, I can just flash what are the various components of the error. So there are 2 components of the estimate of error that came from estimating how good the convergence of the approximate is. And that we did in 2 ways. One is to use this arbitrary parameter in the Borel transformation, which is supposed to give exactly the correct answer back if you know the full asymptotic series. But of course, if you truncate, then the answer depends on your truncation. So we use this arbitrary parameter B, we varied it, and we checked how stable the answer was. So that's one component that we put in the error. Another component is just taking the difference with lower order Pades. And finally, we added by hand a non-perturbative correction inspired by normal on type contributions and of the form e to the -2 beta naught, the one loop beta function times A. Okay, and then we just sum these contributions. So in most cases, this is the dominant one, this estimate of the non-perturbative error, but actually for the gauge kinetic operator, we find that also the convergence instead is the dominant contribution. And of course, I stress once again, it is just an estimate of the error. It's not rigorous at all. Okay, so this is the summary of my talk. So we found some evidence from resummation of epsilon expansion that the fixed point survives up to 5 dimensions for SU2 QCD with number of flavors less than or equal to 4, and for pure Young-Mills with number of colors less than or equal to 4. And here I just put some tables from our paper about the values of the observables. And so that's all. This is a quote from Peskin's paper. And maybe so for the backup slide, we can wait after Joao or now. I don't know if Slava still wants to.
So I don't know whether we should wait for Joao, but there is a one would expect the theory in 5D if it exists to have a U1 global symmetry.
Yes, that's true.
It comes from the topological.
Instanton, yeah, the instanton current. Yes.
The instanton current. Now,
Can someone explain more about this?
Yes, it's if you take trace F mu nu, F rho sigma, and you contract it with a 5-dimensional epsilon tensor, this is conserved due to Bianchi identity. So it's a conserved current in 5D. And what was the question, Leonardo? Sorry.
So of course, these local operators are all neutral under this U1.
Yes.
But in principle, you could try to access the charge sector by trying to construct some sort of instantonic operator.
Yeah.
formulas epsilon
agree.
dimension. This is
Yeah.
something that has been done, I think, in formulas epsilon dimension by Silvia and collaborators.
Yes,
for,
yes, I agree. Yeah.
storing 3 dimensions.
Yeah, one could use a similar method to what they did for the monopole operators in epsilon expansions, and perhaps a similar strategy could work in 4+ epsilon for these instanton operators. I agree.
So in the supersymmetric case, as you know, there's this very strong check because the naive flavored symmetry is SUNF, but then the prediction is that it actually gets enhanced.
Yes.
Because these instantonic operators become in the same multiplets. And so I don't know, of course, what is the expectation for the non-supersymmetric case, but that would, if you could check that, that would be a very strong qualitative check that things are.
So, I mean, just one thing. One check that one could do to start with is whether this operator has the right dimension to be a conserved current, okay? And that, I mean, I just realized—
Isn't that sort of guaranteed? Sorry.
Huh?
Isn't that sort of guaranteed? No.
It is.
Maybe only in the supersymmetric case. Okay.
I mean, it is sort of guaranteed, but it's still kind of non-trivial, the requirement, because what it needs to be true for this to happen is that the operator trace f mu nu, f rho sigma with all antisymmetrized indices in 4 dimensions must have a very particular anomalous dimension, which is the one that then allows you to get the correct value. And this happens. I mean, this is true. Okay, that's not so strong check, but it's true.
Can someone explain why, is there intuition why this, I mean, it's easy to understand that when you crank up NF, then these theories, they will stop being CFTs in 5D, but for fixed NC. But what is the intuition that if you just crank up NC with NF, keeping NF 0, then at some point this theory ceases to be CFTs in 5D? What's the reason for that?
I mean, I don't know that that's true. I just know that with our methods, we lose control at some point, but I don't have any reason to actually think that there is upper critical value of NC. So I can tell you the technicality of why at some point we lose control. Basically, the statement is that the value of the critical gauge coupling keeps becoming smaller and smaller as we increase NC, but our error bars basically stay constant. So at some point, 0 becomes in the allowed range.
But do you see some sort of turnaround in the behavior of this fixed point gauge coupling as a function of epsilon, like that it first grows and then starts decreasing just for the central value, or is it? Because I saw some your NF equal to beta function, it was showing some tendency to kind of, not beta function, but the one of the first plots that you showed, maybe the very first one. So here it shows that first this gauge coupling grows with the function with epsilon, but then it has a tendency to stabilize. So is it what happens for a larger NC? Does it stabilize and then starts coming down, or does it just stabilize?
Well, maybe Fabiana can correct me if I say something wrong, but my memory is that we just get a very similar figure, but the central value gets lower and lower, okay? And then the error bar just stays approximately constant, and then at some point we lose control.
Yes, that's true, but it actually doesn't stabilize for higher epsilon. It's like up to, it is 0.6, but like for 1, epsilon equal to 1, and like the other part of the graph which is not showed, it's
growing
actually, again. Yes.
Okay. Okay, maybe I should at this point stop sharing and leave it to Joao.
Is this the coupling that you show, or the Hooft coupling?
No, the coupling. There is no just G squared. Yes.
So there's no, so these theories, they stay even if there's no notion of weak coupling appearing for large NC.
No, there is no simplification. I mean, you still have the fact that planar diagrams will dominate, but I mean, that's not very practical in any case. I mean, I don't know of a way to use that to get information about the fixed point.
Okay, then let's get off to João then.
But maybe we should thank Lorenzo first for his.
We can thank Lorenzo. And I was hoping to thank you both. Maybe Lorenzo will contribute again later, but let's thank Lorenzo for sure.
Okay, so let me try to be brief. Not everyone is probably very tired by now. So this is, I'm just going to report on some rather simple-minded approach to this problem on the lattice. So this was work done with Adrian Florio, João Viana Lopes, and José Matos. And basically it was the master thesis of José Matos, and he wrote the code and ran all these simulations. So really that's the hard work is his work. So so now you know the setup. So the motivation is epsilon expansion says that this UV fixed point should be there and probably only has one relevant deformation. Therefore, the critical surface should be codimension 1. So it should be relatively easy to find on the lattice, right? You just move one parameter until you hit this critical surface. You just have to go in the right direction. So you have probability of order 1 of finding it, okay? So that was like the most naive idea for the motivation for this project. And there is not much literature about this exploration. So we decided, let's try to do it. So as Lorenzo explained very well, we know how to find free Yang mills very easily, right? You just do the standard lattice action and we go to weak coupling and we will flow in the IR to free Yang mills. The question is if we can find some lattice trajectory that actually intercepts the critical surface so that we can find this UV fixed point. So let me review for you what happens if you just take the Wilson lattice action, just simple plaquette action. Okay, so well, all of you know this. So this is just a simple plaquette. You have link variables in SU2, and the coupling is this beta in front of the action. And so clearly, as you go to very large beta, which corresponds to weak coupling in the G-square notation, you go to this deconfined phase. So here, you know that you will be in the free Yang mills phase. And then when you go to small beta, well, you can call that a confined phase. So for example, well, there's several. I mean, you can actually measure an order parameter like the Polyakov loop, but it's easier to measure just the expectation value of the simple plaquette and what you observe in 5 dimensions. And so this was first observed by Kreutz in 79, I think in a 4x4 to the 5th lattice or something like that. That was the biggest he could do. It's first order. So you observe some hysteresis curve that if you come from high beta or from low beta, it's a first order transition. So this action did not hit the critical surface. Okay, so somehow this one does not work. Okay, so that's the status if you just take this action. So of course, what we tried to do was to modify the action a little bit so that we could find the critical surface. But before showing you that in terms of models, I want to just remind you a bit of entropy, like because we have to distinguish first order from second order phase transitions. So for that, it's easier on the lattice. I mean, here you have hysteresis, so it's quite difficult if you just do fixed beta Monte Carlo simulations. So we use a slightly different method to do that. So essentially the idea, so here I'm writing the partition function on the lattice. And this should be the Euclidean action. And I'm writing it as beta times E in analogy with statistical mechanics. So, okay, so it's clear that E here would be just this, this quantity. This would be what I'm calling the energy. And I mean, by trivial rewriting, you can define the entropy. So the number of configurations that have a given energy. And therefore, then in thermodynamic limit, this will be dominated by saddle point. And so you can have this entropy. So in this system, entropy just means the number of configurations with a given action, okay? The given energy E, which is the action. And what we do in the lattice is to actually measure this entropy. And why is that? Because, well, you know from your statistical physics that if it's a first order phase transition, the entropy will have this kind of behavior. And this jump, well, if you remember, when this area is equal to this area, it's actually the critical the critical coupling, and this jump is what we call the latent heat. So if we can measure this on the lattice and we see this kind of inversion of the first derivative of the entropy is negative and there's a positive region, we already know it's first order. While for second order, the derivative of the entropy should not change sign. Okay. Well, in fact, it's a bit subtle if the second derivative of the entropy is related to specific heat, and there is a qualitative different behavior if the relevant information is above or below the over 2. So for example, for the Ising model, delta is less than the over 2 to 3D Ising, and so you have divergence in the specific heat. So this is, you observe one type of behavior. If delta is greater than the over 2, like for example for the O2 model, then the specific heat does not diverge, right? You have the lambda point, and then basically this curve will be dominated by the regular piece, and you have to just notice that there's some subliving hidden non-analyticity inside, okay? But so, yeah, just to remind you, this is first order, and if it doesn't change sign, it could be second order, but it might be difficult to find the transition point. Okay, and we expect to be on this case using the estimate that Lorenzo said. We expect to be more like the O2 model in 3 dimensions than the Ising model. Okay, the specific heat should not diverge. Okay, any question about this general story? If not, I will just tell you the models. So first thing we tried was just exactly what was first tried by Kawai, Nio, and Okamoto in '92. So they just said, well, let's take the fundamental, the action, the Wilson plaquette action, and add an extra coupling where you also consider plaquettes in the adjoint representation. Okay, I mean, in fact, this is just the square of the plaquette in the fundamental. So, okay, it's just a new coupling in this action. So now you have two couplings, beta F and beta A, and you have a bigger chance of hitting the critical surface. So first thing we did was just a very rough picture of the phase diagram with a small lattice, L equals 4, so 4 to the 5th lattice sites. And here I show you, okay, you see the color coding. So this would be, well, this W1, W fundamental and W adjoint for the expectation values of the plaquette in the adjoint and then the fundamental. And well, I guess what you should keep in mind to have some reference points. So beta A equals 0 is this line here. So this was what the standard pure Wilson action, and this was a phase, the first order phase transition we saw. And what you see is that this first order phase transition, if you now look, for example, here at beta equals -3, the transition looks much more smooth. Okay, so what Kawai did was, let's say, let's investigate this transition here to see if it now became second order. Okay? And we just try to reproduce his results with more precision. so here are the plots for the entropies. Okay. Okay, I mean, this is a bit of details, but this is the effective entropy if you work at fixed beta joint, the adjoint coupling, and just vary the fundamental coupling. Okay, so we did one-dimensional scans, like I'm explaining here, one-dimensional scans of this two-dimensional phase space. And essentially, what we find is that it's always first order, but the latent heat decreases. Okay, so that was what Kawai saw. You saw the latent heat decreasing. I actually have a picture of the latent heat here. As you move in beta A, so at fixed beta A, it's always first order, but it's harder and harder to see that it's first order because the latent heat becomes very small. So you need to go to bigger lattice sizes. So this was the main result here. It was a negative result. Let me just tell you something which I still don't understand, is that if you look, for example, here at this curve at beta A equals -3, you see that when you increase the size of the system, the curve doesn't seem to be converging. I mean, what you expect in a standard first order phase transition, this curve just becomes a curve that is fixed in the thermodynamic limit. Here it seems to be that this derivative is increasing with the size of the system. So we actually computed the second derivative of the entropy, and you see that as you increase the size of the system, it seems to be diverging. So this is some strange behavior. I don't know if anyone knows a system like that there is an unstable region that instead of just being some fixed curve, the curve is still, there's some kind of critical behavior hidden in the unstable region, which, yeah, I never saw a system like this. I don't know if it's really diverging or if it's just, it will stop at some finite size. But yeah, I wanted to bring it up because it's one question we don't understand.
But can it happen that this entropy function in the limit of infinite volume is discontinuous as a function of energy? Or is there some general argument that it can never happen? Because it looks like that's what you're saying. You're saying that in the limit of infinite volume, this function is going to become discontinuous with a jump. So the latent heat is going to be 0. And there's going to be a finite jump in the entropy.
Yeah, I don't know of any system like that. I think it shouldn't happen, right? Because the entropy is like related to just free energy and the energy. So all these quantities should be continuous. Only the derivatives should be discontinuous. So I would be surprised. I don't know any system like that. But if anyone has a similar example, I would be happy to hear about it. Okay, let me continue. So this was first exploration. So then, since it didn't work, we tried another model. So another very simple-minded variation. So here, what we did is we added, so we had the standard plaquette term, and we added now a term still in the fundamental, but 2 by 2. Okay, so a bigger plaquette, like a next to nearest neighbors interaction, if you want. So now again, you have two couplings, beta 1 and beta 2. And again, we did some first exploration of the phase diagram with a small system size. And here it is hard, actually. So there is this region here, which basically the simulations don't converge. I think here, we think it's basically like a spin glass, that there's frustration and it's very difficult to converge the simulation, the Monte Carlo simulation. There's like many local minima and it is not converging. But again, if you look, so again, this is the standard Wilson plaquette action. And now again, what we did was to explore another cut here with beta 2 constant and see what happens to, again, this phase transition. And so this is the result, the best result we have. So we choose beta 2 equals whatever, -0.22. And here I'm showing you again the first derivative of the entropy. And we see here, we up to L equals 12, which is the biggest size we can do. It's 12 to the 5th, so it's a lot of lattice sizes, lattice sites. We don't see sign of an unstable region. Okay, so here it is compatible with a continuous phase transition. The first derivative of the entropy is monotonous. And here I show you the second derivative, and you see that there is some peak in the second derivative, but it stays negative. I mean, of course, it's very difficult to extrapolate with L at 12, but that's the state of the art. And maybe this picture is my last figure. So if you just look at the maximum, okay, so if you look at the value of the maximum here, maximum of these second derivatives as a function of L and for different fixed values of beta 2, you see when beta 2 is, if beta 2 is 0, this maximum becomes positive and you have a first order phase transition. But if beta 2 is like sufficiently negative, we never observe the maximum second derivative becoming positive, which is compatible with a continuous phase transition. So, well, you can judge from the size of these error bars that this is extremely preliminary, but that's the state of the art that we could do. Okay, so that's all I wanted to say. So I would say the search continues for the lattice model that gives you this UV fixed point. And the two points that we are focusing that we would really like to understand is this critical behavior that I mentioned in the unstable region, and this transition in the model 2, which, so what we're trying to do now, we want to also explore the transition in this direction, because it seems that really the non-trivial physics is happening when you go between the deconfined phase here, this is deconfined, and this strange phase that that is down here. Okay, this is all I wanted to say, and I think now we should continue with the open discussion about what else we should try to find this fixed point. Thank you.
Thanks, João. Yeah, what should we try? Does anyone have any suggestions?
I think it would be nice to hear a bit more about this supersymmetric approach, where they really gave a proposal of how to find it, if Lorenzo wants to.
Sure. I mean, perhaps I created too much expectation for my backup slide, but I can show it. Oh, where is it? Sorry.
And then I think that we should also think indeed of the conformal bootstrap.
Yeah, exactly.
What would be the simplest setup to just look directly for it with conformal bootstrap? We had a talk by Yin Chen, right, telling us what are the good strategies to find gauge theories with the bootstrap. So this is another candidate.
So can you see it?
Yes, we can.
So maybe I can just illustrate. I think the most interesting thing is this figure on the bottom right. So there is a phase diagram with E1. It's the name of this superconformal field theory, which is the one that UV completes the SU2 Young-Mills, SU2 supersymmetric Young-Mills. So it's the case without flavors. And so there is this x-axis is just the gauge coupling, and if you move in this line, you just have super Young-Mills on both sides, okay? And then there is a supersymmetry breaking deformation. And what these authors do is that they show that if you, so with this supersymmetry breaking deformation, we can flow from super Young Mills to Young Mills on both ends on this phase diagram. And there is a U1 times U1 global symmetry. So one of these U1s is the instantonic U1 that Leonardo was mentioning before. And there is another U1 which doesn't act on any operator of this non-supersymmetric Young-Mills theory, but it exists in a generic point of this phase diagram. And this is a subgroup of the SU2 R symmetry that exists in 5 dimensions. And what the authors showed is that there are different contact terms for the background gauge fields of these two U1s on the two sides of this y-axis. Okay, I don't know if if it's understandable what I'm saying. So since there are these two different contact terms, then they argue that there must be some phase transition in between. And as far as I understand, they don't give a lot of evidence that this transition should be second order. They just say that some transition, there should be some kind of transition, but okay, that's the proposal. That's as much as I understand this proposal. I don't know if somebody.
But this, if I look at this picture, then this CFT seems to be implied to have two relevant deformations, because there's one vertical.
No, the one vertical is irrelevant for the
The one vertical is irrelevant,
from the point of view of this CFT. So this CFT only has the gauge coupling.
Yeah.
The one interesting thing is that it seems like you have Young-Mills on both sides, right? So it would seem like there is Young-Mills, then there is this transition, and then what before I said that should be the confined phase is that they had another Young-Mills at low energies, just with some different contact terms. So
this is a very interesting observation for potential lattice searches.
So it seems like
because this would imply, this would imply that one should look for some lattice actions which
have Young-Mills on both sides.
Which have Young-Mills on both sides. So it's kind of weird, yeah.
But Lorenzo, the first order line can end on a second order point.
Which first order line, sorry?
Just in general, the first order line can end on the second order point. So it could be that this vertical line is first order. I don't see any evidence otherwise.
Yeah. So that's what I said. I don't know that they give strong evidence that this transition is actually second order. They just say that there must be some transition.
Yes, that's clear because of the SPT phase.
Exactly. So they say that these are two different SPT phases, and therefore there must be something in between. And in my opinion, they don't give a very strong evidence that this must be second order. Yes, I agree with you.
Well, there's a question: strong evidence versus any evidence.
Well, I don't want to maybe not make justice to what they say, so you can see for yourself what they say in the paper. They give some argument. In my opinion, it's not very strong.
Okay.
But yes, let's say that this interested me in the problem, and then that's why we started reconsidering also the epsilon expansion.
But from the epsilon expansion, can we learn anything about the phase on the other side? Not really, right? Because it just flows to strong coupling. So
yeah, I mean, not that I know of. I mean, I have never seen studies of the full phase diagram using epsilon expansion. I've just seen going to the fixed point, but I don't know, there might be ways.
What you can try to do is to try to compute the effective potential for F squared. Try to get some hints from the epsilon expansion.
And sorry, the effective potential for what again?
For F squared.
because you suspect that this operator should get above or something. Sorry, I didn't understand why the effective potential.
Right. So we, well, one way to see if it's first order or second order is to add the relevant deformation, but at the same time compute the potential for this guy.
Mm-hmm.
So it's an interplay between. As you said, the epsilon expansion shows the fixed point. So
Yes, yes.
This
So you suggested one way to go a bit away from the fixed point, and
yeah. I mean, I don't see how that's going to work. What I would try to compactify on a large circle, on a very large circle.
Mm-hmm.
Because it doesn't prove anything, it wouldn't prove anything, but if you can show that in 4D it's second order, that would prove something. So it can prove something only if something. So if you compactify on a very large circle and you can understand whether the 4D transition is second order, then you're done. Because if it's second order in 4D, it must be second order in 5D on a very large circle.
Mm-hmm.
But first order in 4D doesn't prove that it's first order in 5D, because the first order line can end on the second order point.
Uh-huh.
So if you manage to understand the large circle theory and you're very lucky, then you might be able to prove something about 5D.
Okay. But I mean, I was also thinking, on the other hand, if we put it at finite temperature, shouldn't there be something that we can say about the high temperature phase, knowing the fact that there is a UV fixed point or not?
Exactly, that's what I said. You can try to study at another axis, which is the temperature, and try to go to as low temperatures as you might. If at very low temperatures, it's first order, you're not done. It might be either way at 0 temperature. But if it's very low temperature, it's second order, then you're done.
How is controlling the theory at very low temperature going to be easier than controlling it at exactly 0 temperature?
Well, because it's 4D, and you might try to argue something. But I agree, it's not very optimistic. I'm not optimistic that this can work. The low temperature theory in 4D might be as hard as the 5D theory originally.
Sorry, what is the proposal again? What is the global symmetry of this flow of the non-supersymmetric CFT that they propose?
It's U1 times U1. So yes,
one of the U1s the instanton charge.
Yes. So okay, I hope I'm remembering everything correctly, but yes, one of the U1 is the instanton, and the other one is a subgroup of the R symmetry.
But then, sorry, why would this be the UV completion? I mean, it's clear how you're going to get one U1 from the instanton charge, but the other U1 would be very mysterious.
Okay, let me.
I mean, from the point of view of starting from pure Yang-Mills.
Well, I mean, as we said before, sometimes there are announcements of symmetries at this fixed points.
The announcements usually happen in the IR, but maybe in the UV too. I don't know. But then the relevant.
Well, I mean, that's for instance what happens in the supersymmetric case, right? We have the flavor symmetry enhances in the UV, or not? I mean.
Well, but but at least the cartons are visible in the IR, right? The cartons are the naive symmetry and the instanton charge. Here, there's a new carton that is completely invisible in the infrared theory. I don't know. Maybe that can happen, but it looks weird.
I think that just once you do this deformation that they talk about, it just acts on the massive states and it goes away.
Yeah, something like that. Yes.
But what's the big deal? If this CFT exists and if it flows to Yang-Mills and if it's not supersymmetric, then it fulfills the rules of the game. We're just looking for some CFT which flows to non-supersymmetric Yang-Mills and which is non-supersymmetric.
Yes.
Because what you call UV completion is a well ill-defined question.
Yeah. It's just some CFT that does that is
Yeah.
very big operation. Yes.
Maybe it's not the only CFT, but
Yes.
I'm a little perplexed by the SRU1, but okay, whatever.
Maybe I should.
we
check.
all are.
I mean, as a benchmark of this whole story, perhaps you could literally just repeat this epsilon sponge for the n equal to 2 case.
Yeah, I think that's a good suggestion. I agree.
And there you should, I mean, ideally, you'd also study these instantonic operators, the one charge on the instanton.
Mhm.
Because the prediction is that they should form multiplets of this enhanced flavored symmetry. So that would be, of course, a very strong benchmark for the epsilon expansion if the two dimensions approximately agree when epsilon is equal to 1.
Mm-hmm.
And as another obvious comment, I mean, here you're just focusing on a neutral sector of the theory doing this epsilon expansion, but clearly, if we were to bootstrap the theory, the charge operator would perhaps be the first place you would like to look at, right? So having some estimate for the lightest charge, for the dimension of the lighter charge operator would be very useful.
But sorry, how adding just the information that there is a U1 symmetry, how does it narrow the problem? I mean, there are many things which
I don't really know, but if you want to bootstrap something, I mean, the first place to start is to not understand the global symmetries, right? I mean,
yeah, for sure there is a U1, yes. That's...
I would probably do the bootstrap of the lightest charge operators as that would be the first thing that comes to mind if you want to bootstrap a theory where you want symmetry.
Yes, okay, I agree.
So what Leonardo is suggesting that, for example, Lorenzo does a computation. Lorenzo and Fabiano do a computation for this monopole, for this instanton operator, and they give some dimension x. And then we do bootstrap with that dimension and U1 global symmetry, and assuming there is only a single relevant perturbation. And then, for example, we find that this x is inconsistent.
Something like that. Or...
Okay. Well,
yes.
Well, we did it several times already. Maybe we can do it again. These kinds of tricks, dirty tricks. But I'm also, this is interesting story. But this story, this Monte Carlo simulations that João has shown. Okay, none of us are experts in Monte Carlo simulations, but it seems that there is something going on there, some physics. What is this? Curves which do not stabilize, this strong volume dependence. I mean, it seems like those curves are telling us something. So I forgot, João, do you advance any suggestions of what could be the reason for this very strong volume dependence that you're observing? Is it unheard of to have such a strong dependence?
By my ears, yes, I think. I don't know. But I want to emphasize that if you just do the simple plaquette action without a joint term, without any adjoint plaquette, you don't see it. So you need to go to some finite value, like the plot I showed you with this very high peak when we put this coupling at -3 or some fixed value of the adjoint coupling, then you do see this peak. But
no, there is a peak, and then there is also a strong volume dependence for the position of the peak.
Yes, it's also
like usually. What do people suppose that this were CFT? Is there some like criterion in the literature which says that if the phase transition, if your system has a phase transition, and okay, it's described by CFT, then if the CFT is of such and such type, then when you do Monte Carlo simulation, you'll see strong volume dependence. And if not, then you don't see strong volume dependence.
But
determines.
Notice that this is in the unstable region. I mean, if you just do fixed beta simulations, you never see this. This is in the region where the derivative of the end, I mean, it's like negative temperature, sorry, negative specific heat. It's the unstable region of the first order phase transition. So
yeah, but the position of this unstable region, how? Yeah, so there are some observables there in that unstable region which seem to be strongly dependent on the volume. Or not. I don't know if it counts as a strong dependence or
not. Yeah,
like,
the slope is a strong dependence, that's for sure. Maybe I can.
also the energy, like the position, the energy. So there was some central energy, and then there was the latent heat, which is the difference between the two, maximum and minimum. But even the central energy was strongly dependent on the volume. How is this possible?
Let me share again so that we talk about something concrete. I don't know, for example, this one.
Yeah, for example, like
on this one.
For example, second plot on the left, I see that.
Sorry, here, yeah.
The value of this plaquette changes a lot.
Yeah, this
yeah.
one.
Yeah, for example. These curves seem to be moving to the left.
Yeah, but that's, I think that is converging. You see they are moving less and less, so that will stop. It's just the derivative that is not converging, that it's becoming very steep. So if you look here in this other plot, which is the second derivative, I think the center will converge, is like moving slowly. But the maximum for these sizes is still growing very significantly, so it's unclear if it will converge or if it will diverge.
But suppose that it's a first order phase transition and you would like to reproduce this sort of behavior as saying, okay, well, there are two states. One has one energy density, another has another energy density, and then you kind of try to mix them. You will never get such curves, right?
I think that, as I showed you, the standard expectation is this in the thermodynamic limit. Without so what we're seeing something that it's becoming here very steep like that, like you were saying, almost wants to be discontinuous, and so this is the question mark. But yeah, this looks, I mean, it looks very different from the original quest. It's just a surprise and some enigma, because it's definitely not a second order phase transition. It's something different. Yeah, I wanted to ask another question. So what if we take this supersymmetric proposal and we like use it to get some inspiration for the lattice? Like we put the theory on the lattice, I mean, but we don't really try to put the full supersymmetric theory exactly on the lattice, but we say, let's say if we put it and then we deform and we integrate out, what would be the leading correction to the Wilson plaquette action that we will get from this construction? Because here we added some couplings a bit randomly, but maybe we could get some guidance. What should be the right coupling to add from these more smart constructions, let's say?
Well, these theories are like vector-like, so perhaps there is a way to put down the lattice. I'm not sure. So, but what you would like to know is what is the effect action.
The leading.
So if you know how to put on the lattice super ion males, let's say, then you could first try to look for the E1 theory.
Right.
And then perhaps move away from there. I don't know.
But that's, I mean, that's going to be difficult because here the initial
Sounds like a
hope,
lot.
yeah, the initial hope is that it was just one relevant operator, so it would be easy to find on the lattice. But if you have to tune many parameters,
I mean, I don't know if you can, perhaps the lattice breaks supersymmetry, I'm not sure, but if you would be able to preserve supersymmetry, then you only have one parameter, right?
if you preserve, okay,
Yeah.
there is some tricks to do that on the lattice, but okay, that's much more,
Mm-hmm.
much more than what I know. Yeah. Okay.
Like if you restrict to supersymmetric deformations, then there is only one that goes from E1 to superhabits.
Yeah, but typically, if you're unlucky, you can at most preserve one supercharge on the lattice, not the whole. I mean, it's usually very.
I don't know anything about supersymmetry on the lattice, so.
Okay. But I mean, isn't it surprising? So what could justify that it's so hard? I mean, we already explored 2 parameter families in this big phase space, right? In this coupling space. So somehow this idea that it's easy to eat the codimension 1 critical surface is not being realized. What is going wrong here? Is maybe there's another relevant operator?
Well, maybe the theory does not exist. I mean, this would be the first example of a non-supersymmetric CFT in dimension greater than 4.
Yeah, I mean, maybe another thing that we should mention that perhaps it's worth exploring if one can disprove the existence of these theories, but I mean, I don't know where to start from, but.
No. But why we being so it's like Zohar said. I mean, we have a first order line, and it can either end on the second order and become second order at some point, or it will stay first order.
Well, I understood Zohar's comments.
So how do we know? So this line is, yeah, it's a long line, and we don't know, you know, which part of that line are we exploring right now.
But it cannot be, right? If it's codimension 1, it should not end on a point of second order phase. It should transform into another line.
Yeah. It should transform into a line of second order phase transitions.
And this is what seems to be hard to. I mean, okay, model 1 seems not to happen. I mean, we followed this line. I don't know, Inia, whatever, which color you want. Yeah.
But imagine that your lines run perpendicular in some high dimensional space.
We followed this line for a long while, and it seems to be always first order, just latent heat is decreasing, but really it doesn't, it's always first order.
It's very typical for codimension 1 first order lines to just end. That's what happens in water.
Yeah, but Zohar, Joe is asking about why is his line? So there are 2. So Joe, imagine your one line that you want to explore runs like this, and it becomes second order somewhere above.
Yeah.
But somehow the lines that you are taking in the lattice, they like kind of run in this direction.
Right, that's true.
So you can run as much as you want, but okay, you shift it a little bit, but as long as you don't change radically the direction of your line, you may never end in the interesting region.
Okay, yeah. So
very interesting. There is an example which is very interesting. Maybe I'll just mention it. It's in 2+1 dimensions. So it has 2 parameters, x and y, and you can establish that there is a first order line somewhere at large x, but at very small x, there is no transition. You can just show it analytically. So people use that to prove that this line must end at a CFT, and then they found it on the lattice. That's why I mentioned this temperature example. Maybe if we have enough directions and we can prove that at least in some directions the lines don't exist, we could maybe show that they must end. But it's very optimistic.
It ends, but it ends at you said the transition below doesn't exist at all, or is it a second order transition below?
It just doesn't exist. That's what happens in some condensed matter magnets. That's how they show that there's a second order transition.
Right, but that would mean it's codimension 2, right? There's two couplings that you have to tune to hit the point.
You're completely correct.
So that wouldn't, yeah. But here, if the scenario is that it's codimension 1, it should be easier. Somehow, okay, Slava is saying it's true. Maybe the line is like that. It's going parallel. The second case, model 2, maybe model 2 is working. I mean, it's just very difficult numeric. So maybe model 2, maybe it is like that. I don't know. But this requires more numerics, and it's not just a matter of working, because we really 5D is very difficult on the lattice, right? Everything is to the 5th power. So here maybe this transition. So maybe the transition here is first order, but then it continues as second order. Maybe.
I think what Lorenzo could do maybe, and Fabiana, is to tell us what is the dimension of the lowest U1 charged operator. That would be very useful, I think. If it's also relevant, we have more chance of understanding something analytically.
Okay, because you would also study the phase diagram with this guy turned on. I mean,
yeah, we could try to build a bigger phase diagram and see what's going on.
mm-hmm.
Right.
Yes, I mean, there is a strategy that Silvio and collaborators use for monopoles.
Yeah, you just do S4 times fractional dimension.
Exactly, yes.
Yeah.
I'm not sure if I'm very optimistic that can be used beyond one loop, but one can at least get first order.
But do it in the supersymmetric case where the expectation is very sharp.
Okay.
But what is the 0 order guess for this dimension?
Absolutely.
I'm not sure.
Because they just don't exist in 4D, right?
Right. Sorry, they don't exist in 4D. They don't exist. So I think what you have to do is to consider in fractional dimension some defect of the form S4 times some, maybe Silvio can correct me if I'm saying something wrong, some hyperbolic space of dimension that goes to 0 when you're in 4D and goes to 1 when you're in 5D. And then on the S4, you put some instanton charge, I think. Is that correct?
This may be harder, right? Because in the monopole case, you were interpolated between S2 times ADS2.
Yes.
And ADS2 times S2 times R.
Right.
Now, ADS epsilon is something that might be a little harder to realize, but I don't know.
Yeah, but if this operator is relevant, then does it mean that Joao will never find his CFT because this symmetry is not microscopically realized?
Exactly, that's why I'm asking this question. I believe it's because typically Wilson lattices do not preserve monopole symmetries. Okay, this symmetry doesn't exist in Joao's construction. So if this is relevant, that could explain everything that Joao said. It's not a symmetry. Then it's not codimension 1 and everything is kind of has to be revisited. That's what would happen if you put any of these quantum magnets on the lattice. If they don't preserve the U1 and there are typically tons of relevant operators.
By the way, it should be easy to check. Some of these operators are protecting the supersymmetric case, so it should be easy to check whether there's a protected relevant operator in the supersymmetric case.
Right. But also the one loop answer would be already a good start.
Yeah.
But really, what is the expectation at 0 order? Is that the dimension is like 1 over epsilon and disappears in 4D?
No, I think that this guy doesn't start his life as a local operator. So in 4D, it's something that only becomes a local operator in 5 dimensions. And I'm not completely sure what is the exact word to define this thing in 4 dimensions. For the case of monopoles, when you go from 4D to 3D, they start their life as line defects, and then they become more local operators in 3D.
I think we can work out the 0th order expectation. It's very easy. So we just have to build an instanton on S4 times S1 and evaluate the integral of f of f. Now, the f of f is normalized by the coupling A star that Lorenzo found. But the 0th order guess is just 1 divided by A star.
You would say it's the instanton action.
Yes, it's just because the instanton action is 1. That's the charge. and the current is normalized by G, which is the coupling at the fixed point. And that's the zeroth order guess. So it's order 1, and it might well be relevant. And if it's relevant, then it explains everything Joao found.
Okay, yeah, that's this zeroth order expectation I could check relatively fast.
But can you explain? So the fact that just the presence of the lattice would generate this kind of relevant operator. So just
Yes, that's what happens in Polyakov's models. This cannot preserve the topological symmetries on the lattice.
Yeah, that would be very similar to 3D QED and stuff like that.
Exactly. So this is what Lorenzo must do, because that will inform the discussion next time.
Okay, sounds good. I have a duty for the summer.
And Fabiana, I don't know.
So actually, I have a quick comment on the lattice simulation. So I think for the lattice gauge theory simulation, there's a trick to suppress the monopoles. Just replace your, at least for U1 gauge theory, you can replace your Maxwell term from cosine to just F mu square, and that will suppress the monopoles. People are using this trick almost in every simulations of this 3D lattice gauge theory. I'm not sure whether this works for 5D SU2 gauge theory.
Wait, but this suppresses them numerically, not analytically, right? If I remember.
Numerically.
Yeah, it's just
the statement is that in the in that setup in the lattice simulation, there's no monopoles. I mean, the monopoles will not generate.
Yeah, but no, I think it suppresses them analytically because we just. But that trick is only possible for the U1 gauge theory. I don't know how to do it for.
Yeah, that's right.
That I don't know yet.
Yeah. For U1, it's very clear that you can just declare that the gauge field is an R gauge field.
Mm-hmm.
Yeah.
Then you suppress them and you win the game. For SU2, there is no way to do that.
I see.
So I'm not optimistic about this kind of scenario.
But people in the old days, people also tried to suppress these monopoles with other more dirty tricks, like those which would work only numerically but not analytically. Like filter your gauge configuration, see that there are no instantones.
Yes.
So there is some hope to simulate. I mean, even if these instantones turn out to be relevant, there's still some hope to do some lattice simulation, but it's going to be a bit more complicated.
Yeah.
And in condensed matter context, usually we have a trick like we can make monopole to carry some discrete lattice quantum number, and then that could prohibit it. Yeah, but that requires a lot of work, and sometimes that will give you a side problem for Monte Carlo simulation.
I see. It's in quantum Monte Carlo simulations, right?
What he's saying, yes, it's typically in quantum Monte Carlo. That's right, not in Wilson's Monte Carlo.
Yeah.
Yes.
So
guys, I'm very happy that we are making progress. That was nice to see everyone for this last discussion of the conference. Great minds.
But I don't know, Slava, before you conclude, I don't know if Ning or Yinchen, they have some more concrete idea following their approach to Bootstrap.
I guess my first question is that if I understand correctly, in your story, the matters are fermions, right? The matter fields are fermions, right?
The matter field. I do puring mills. I was just doing pure.
Okay, then that's in Lorenzo's story, right?
I also consider things with Dirac fermions. Yes.
Yeah. I'm wondering whether there's a version for that matters are bosons.
Yeah, in principle, yes. Why not?
I think that would be easier for conformal bootstrap. Yeah, fermions are much harder, and in particular in 5D, fermions are the spinor rack of your SOP.
But the fermions, the fermions are you need to construct gauge invariant operators.
Yeah.
So I don't think we are worried too
Well,
much.
the thing is that the operator content will be very different. For fermionic theory versus bosonic gauge theory.
Mm-hmm.
And so if it is, let's say SU2 gauge field coupled to bosons, then yeah, we can immediately do some simulations for that. And
so you mean that you would use some gauge invariant operators made out of the scalars, and you think that's promising?
Yeah, for SU2 gauge field.
But how come it's easier with the composite operator made of scalars rather than composite operators made of fermions? Sorry, I don't know.
Yeah, so it was discussed in our paper, that just about how some general some roadmap to bootstrapping critical gauge series. So the idea is that for different rank of your gauge group, the operators will be heavier. Like, let's say let's say if you talk about SU2 gauge field versus, let's say, USP4 gauge field or USP6 gauge field, then some operators in the SU2 gauge field gauge series will be heavier than other gauge series. So that could be used as a very good, that can be used as an input for you to exclude all other gauge series. And that turns out to work well for both scatter QED and SU2 QCD in 2+ epsilon dimensions, as well as in 3D. Yeah, in our paper, we only published results about scatter QED, and we have almost identical results for SU2 QCD, but we just too lazy to write it down. Yeah. So yeah, I'm not sure. Yeah, and it would be interesting to say whether this could also work for 5D SU2 gauge field coupled to bosons.
Okay, I see.
Yeah, that's very interesting. But what about the case without matter? Would then that method doesn't work, right? You can only
right. Then our approach won't work for them.
I see.
In other slightly orthogonal direction, if you're in the business of benchmarking the epsilon expansion, would be to look at large n supersymmetric examples where I believe some of them have ADS duals. So you might actually be able to compare anomalous dimensions with the supergravity results.
I see. Okay, that's interesting.
Any further comments? Well, what should I say? It was a great finish for our program.